Why is feedback crucial for system stability in control systems? Imagine trying to keep a bicycle balanced without looking at the road or adjusting the handlebars. It's nearly impossible, right? That's similar to how control systems stay stable. Feedback acts like your eyes and hands, constantly making adjustments to keep everything steady. In electrical engineering, especially in signal processing and control systems, feedback is the key to making sure systems behave predictably over time. When a system is stable, it means that if you give it a command or disturbance, it won't go wild or oscillate uncontrollably. Instead, it will settle back to a desired state. Control systems usually have a process or plant, a controller, sensors, and actuators. The sensors measure the output and send that information back to the controller. The controller compares this actual output with the desired input, then makes adjustments. This loop continues, allowing the system to correct itself constantly. Without feedback, the system would just run based on initial settings and could easily become unstable if conditions change. Feedback helps correct errors by reducing the difference between the actual output and the target input. For example, if a robot arm moves slightly off course, feedback detects this and adjusts the motors to bring it back on track. This correction prevents small errors from growing larger and causing instability. Feedback also influences the system's dynamics by changing how the system responds to inputs. It shifts the poles of the system's transfer function, which are mathematical points that determine stability. If these poles are in the right place, the system remains stable. Feedback can move these poles into the left half of the complex plane, which is where stable systems live. Another important role of feedback is improving robustness. Real-world systems face uncertainties, like variations in component values or external disturbances. Feedback helps the system stay stable despite these uncertainties. It creates a balance between performance and stability, so the system can handle changes without losing control. Engineers analyze how feedback affects gain and phase margins, which are measures of how close a system is to becoming unstable. Using tools like Bode plots, they can see if the system has enough margin to prevent oscillations. Feedback also extends the system's bandwidth, meaning it can respond effectively over a wider range of frequencies. Plus, it reduces the impact of noise and disturbances, making the output more reliable. In electrical engineering, feedback is used everywhere: in amplifiers to stabilize gain, in oscillators to control frequency, in robotics for precise movement, and in aerospace for safe navigation. Negative feedback, which reduces gain when needed, is the most common because it keeps systems stable. Positive feedback, on the other hand, tends to increase gain and can cause oscillations if not carefully controlled. In short, feedback is what keeps control systems from spiraling out of control. It corrects errors, shapes how the system responds, makes it more robust, and ensures it operates reliably. Without feedback, many electrical systems would be unpredictable, oscillate, or even fail. That's why feedback is the backbone of system stability in control systems.